Remember, in type 1 and type 2 electrolytic cells, the electrodes were always inert. Type 3 electrolytic cells involve electrolysis of aqueous or water solutions using electrodes that can be reactive metals. We'll start with a power supply, wires, and a container, and we'll attach a copper strip to the positive terminal, which becomes a copper anode. And we'll attach an iron strip to the negative terminal of the power supply, which becomes an iron cathode. When the switch is closed, the power supply takes electrons from the copper anode and pumps them onto the iron cathode. So the anode becomes positive and the cathode becomes negative. We'll simplify the electron symbols on the electrodes. And we'll add a 1 molar copper 2 sulfate solution to the container. The copper and the sulfate ions are moving randomly in the solution. But this solution is aqueous, so we can also show some of the water molecules present. Now we'll focus on the iron cathode. Remember, reduction takes place at the cathode. So water may be reduced, or copper 2+ ions may be reduced. But in this type 3 cell, the cathode is not inert. We have an iron cathode. So the question we ask ourselves is, can the iron cathode itself be reduced? The answer is no. Metals in metallic form are composed of neutral metal atoms. Metal atoms will not gain electrons to become negative metal ions. Negative metal ions cannot be formed. Metal atoms tend to lose electrons, not gain them. So metal electrodes are never reduced. And we can say that the cathode metal is never reduced. Also remember that reduction is all that occurs at the cathode. Oxidation never occurs at a cathode. So we can say that the cathode metal is never oxidized. Because the cathode metal is neither reduced nor oxidized, we can say that the cathode metal never reacts in an electrolytic cell. So even though our cathode is iron metal, the only possible species that can be reduced are water or copper 2+ ions. So using this diagram, we'll ask whether copper 2+ or water is reduced at the cathode. Remember, at the cathode, any cations above this overpotential arrow will be reduced from aqueous solution, even if water is present. And any cations below this overpotential arrow will not be reduced from aqueous solution. We see that copper 2+ ions are higher than the overpotential arrow for the reduction of water. So copper 2+ ions will be reduced at the cathode, which we can show here by putting a check mark by the copper 2+ and an X by the water. So the half reaction occurring at the cathode of this cell is Cu2+ plus 2 electrons gives copper solid. Now we'll focus on the anode. Remember, oxidation occurs at the anode. Because the anode is positive, it will not attract positive copper ions. So one candidate for oxidation is water. Another candidate is the sulfate ion. But the anode itself is not inert. It is the metal copper. So the question we must ask is, can the copper anode itself be oxidized? The answer is yes. Metal atoms can be oxidized and lose electrons to become cations. So we have 3 candidates for oxidation at the anode: water, the sulfate ion, and the copper anode itself. Going back to this diagram, we'll represent the anode with an A+. And the possible candidates for oxidation at the anode are water, the sulfate ion, and the copper metal anode itself. But we don't know which one of these 3 species will actually be oxidized. Looking at the reducing agents on the right side of the reduction table, remember that oxidation potentials increase as we move down this side. It's the same thing as saying that reducing agents get stronger as we move down the right side. Remember, oxidation potentials of the reducing agent shown here are these numbers with their signs switched. So the oxidation potential of the sulfate ion, SO4 is negative 2.01 volts. And neutral water, because of the overpotential effect, behaves like its oxidation potential is negative 1.38 volts. And copper metal oxidizing to copper 2 plus ions has an oxidation potential of negative 0.34 volts. So we see that copper has the highest oxidation potential of all three of these species. Its oxidation potential is negative 0.34 volts, much higher than negative 1.38 or negative 2.01. So we know that water and sulfate won't be oxidized, but copper will. So we'll write a check mark by copper. So now we know that the half reaction at the anode is the oxidation of solid copper metal to produce copper 2 plus ions. So to summarize, for this type 3 electrolytic cell, we see that copper 2 plus ions and water are the candidates for reduction at the cathode. And the three species, water, sulfate, and copper metal, are candidates for oxidation at the anode. Using the left side of the reduction table, we are able to see that reduction of copper 2 plus ions takes place at the cathode. And using the right side tells us that oxidation of solid copper metal takes place at the anode of this cell. So looking at the diagram of this cell, we can show that copper 2 plus ions are reduced at the cathode, and copper metal, the anode itself, is oxidized. And it's very important to remember that for a type 3 electrolytic cell, it doesn't matter what metal the cathode is made of. The cathode metal never reacts, so there are no half reactions involving iron in this case.